Hi, welcome to another edition of Linear Algebra. Today we are going to start our discussion about 3 by 3 matrices and their eigenanalysis. So that's the topic for today. We are going to start with a 3 by 3 matrix and then go down through all the steps of finding the eigenvalues, eigenvectors, and perhaps eigenspaces. Well, what is this thing good for before we start it? Well, based on the example we have been talking about multiple times throughout the semester. If you go to this oscillation problem, if there were three balls, like there was another one is somewhere in the middle, and then four springs, uh, to figure out how that thing is going to move, we would need to do analysis of a 3 by 3 matrix. So the size of a matrix comes from a number of interacting particles in your system. That's the reason for the size. And then we have to just go through all the steps we did before. Now we are going to start with some rather friendly examples where there wouldn't be too much complication in it. But as we said before, one of the main steps or main challenges in this is to solve the characteristic equation that comes up. Characteristic equation is going to have a degree which is same as the size of the matrix. So for 3 by 3 matrices we have to solve a cubic equation. Yeah, cubic equation, well, is a challenging equation to solve. We are going to look at problems that are relatively easy to solve. Let's go ahead and do a few examples and see how this works. Okay, so for example, I'm going to pick a matrix M. Let's say 4, 0, minus 2, then 4, 2, 3, and say 5, 0, minus 7. So our objective is to find eigenvalues, eigenvectors. Once we find these two, we want to check to make sure our algebra is correct, and perhaps say a few words about the eigenspaces. Okay, the steps are exactly like what we did for 2 by 2. It's just that there's going to be more work to do. So step 1, let's see. This is step 1, 2, and 3. So step 1, we go after finding the eigenvalues. How does that come about? That we explained this thing before. The determinant of m minus lambda times I equal to 0. That equation, which is called the characteristic equation, is going to have three roots. Those three roots are called characteristic roots or eigenvalues. So we get the first thing out of the way from here. Well, how does this go? Lambda I means lambda times identity. That is to be subtracted from the diagonal entries. That's easy to do. The determinant of, so 4 minus lambda, 0 minus 2. This is 4, 2 minus lambda, 3, 5, 0 minus 7 minus lambda. That whole thing, we want to find it out. Set it equal to 0. Okay, step 1. How do you calculate the determinant of 3 by 3? We explained many ways of doing that. You're advised to look for shortcuts to make your job easier, otherwise these problems can go on and on and on. So here we say one of those shortcuts we talked about is that if you have lots of zeros on a row or a column, go after expansion based on that. Okay, because that makes your life so much easier. So you remember associated with any of these matrices, we had a checkerboard sign. So we just remind ourselves what the signs are going to be, and here are the signs I'm going to use here. So 0, first entry, 0 times the determinant of whatever is left. I don't need to actually bother with writing these things, but just to explain to you what the steps were. This 0 we have to multiply with determinant of what is left is 4, 3. So what we do there is that we take the row and a column that go over that number, and then remove everything. What is left is 4, 3, 5, minus 7 minus lambda. We have the number 0. We also borrow the sign from here, so that is that. Sorry. Then next item, sign is plus. The entry is 2 minus lambda. Let me go ahead and erase this. And okay, so when we pick on that, we erase the row and column that contains it. What is left here, this one we do need to write because it's not going to be 0. So it's going to be 4 minus lambda minus 2, 5, minus 7 minus lambda. And then last one is 0. That sign for it is minus. Then I have to multiply by the determinant of whatever is left. Again, we are wasting effort here because whatever it is here is multiplied by 0. It's going to be 0 anyway, but just as a matter of a practice, I'm going to go along with you on here. So this row and a column, we have removed them entirely. What is left is 4 minus lambda minus 2 and 4 and 3. Okay, after we did all of this, we come back and say, well, you wasted your time even writing this thing. This is 0 because this is 0. And so this is 0 because this is 0. And we are solving an equation. We want this whole thing to be 0. So since we want to solve an equation, we love the fact that this is already factored. So let's go ahead and write it out. 2 minus lambda times determinant of 2 by 2. 2 by 2 was easy. So I multiply these two, 4 minus lambda times minus 7 minus lambda, and multiply these two. I put everything in parentheses so I wouldn't make a sign mistake because it's very hard to recover from these errors. Okay, let's go clean the big parentheses. So I have lambda minus lambda times minus lambda, that's lambda squared. I have plus 7 lambda minus 4 lambda. Let me write it out. Plus 7 lambda minus 4 lambda, then minus 28, and this is all plus 10. 2 minus lambda, let's clean up. Lambda squared plus 3 lambda minus 18. Now again, remember we were trying to solve an equation. For solving an equation, we want to have it factored. So it's not going to be a smart idea to multiply these two. If you do, you are going to set yourself back 10-15 minutes trying to come back to where you are right now. We want to factor, so we leave this thing alone. 2 minus lambda. So okay, factorization of this thing easy. Lambda, what is that? Lambda minus 3 times lambda plus 6 equal to 0. Okay, so we got super lucky here, really lucky that we neither felt the pain in calculating this determinant, nor did we feel the pain in finding the roots of a cubic. Here's the factorization just popped out. So as problems go, this is super special, super simple, because of the way that those zeros were at the beginning. Okay, what are the roots here? Is set each of the factors equal to 0. Let's start from the smallest root. So that's how WebAssign is going to show it to you. labels this thing smallest, and then of course lambda 3 is going to be the largest, and you have the middleman here too. That one doesn't get to have any label, kind of stays by himself. Okay, so we did step 1, find the eigenvalues. These are 3 eigenvalues. Next step, we are going to check to see that these are actually true, but if you want to check it, you can put it back in your equation. Step 2. Step 2, a bit more involved than step 1, is finding eigenvectors. Eigenvectors of our matrix. What did we call our matrix? M. Eigenvectors of matrix M are same as what we call null vectors of M minus these lambdas. So what does that mean? Well, it means that I need to rewrite this thing down here so that I don't go back and forth a lot. So M minus lambda is that matrix we had up there. So let me just write it 4 minus lambda 0 minus 2 4 2 minus lambda 3 5 0 minus 7 minus lambda. Okay. Now we are going to take turns, one at a time. Take this lambda, put it here, and then find the null vector of that. What does that mean? Let's first of all say M minus 6. If you want to put an identity, it doesn't matter. Some books put, some books don't. So this one would be what? Lambda is minus 6. Be very careful in that subtraction so that you don't accidentally think that okay, so 4 minus 6 is going to be 10. 0 minus 2, these are staying. 2 minus 6 is 8. 3 5 0 minus 7 plus 6 is minus 1. Okay, what do I want to do? I want to find the vector that when it multiplies this becomes 0. That would be same as the eigenvector of the original matrix. So what I want to do is to solve the following. 10 0 minus 2 4 8 3 5 0 minus 1 times what vector? X y z is gonna give me zeros. So for this, lambda is equal to minus 6. To find its eigenvector, we put minus 6 in this M minus lambda. Carefully did our subtraction. Now we are finding the vector that when multiplies this thing will be 0. Okay, 3 by 3, a bit more work than. Well, the 2 by 2 was easy. 2 by 2, the equations were multiples of each other. You just picked one, you looked at it, and then you had your answer. Here, a bit more involved. If you can solve it by inspection or quickly, be my guest. Here we advertise something here, our Gaussian elimination software. So I go ahead. We said when you have a homogeneous equation right hand side, you don't need to bother with that last row or last column of zeros. So we just go ahead and enter our numbers here. So we had what? We had 10 0 minus 2 4 8 3 5 0 minus 1. Are we on the right track? Let's go double check. I forgot what we had there. Yes, 10 0 minus 2 4 8 3 5 0 minus 1. I didn't bother to enter these zeros because with zeros, whatever you do, all you get is zero. So with homogeneous equation, you can reduce a little bit by skipping those zeros. We know they are all going to be zero. So now what do we do? Well, we reduce this. Where were we? Sorry. We reduce this. Okay, so resume to go back to. Okay, how do we reduce? Let's make them. I try to do row reduction as far as we can. I divide by 10 here. Okay, and then I use this as a pivot. You remember that? To eliminate this, use this as a pivot and eliminate this. The fact that we got all zeros in one of these rows means we are on good company. We are on the right track. If it did, it means somewhere we typed the wrong thing and we have to start all over again. So this zeros here is a good sign. It has to be like that. Let me go ahead and make this thing identity as well. Okay, so we reduced this. We reduced it as far as we could take it down. Now we have this matrix. Let me write it down so that we do the rest of it on paper. So we did the reduction 0 1, and the last one is the peculiar number 19/40, and down there is our good sign. Good luck sign here is that we got a row of zeros. Otherwise, means something's wrong. So we took this, we did Gaussian elimination on it. It became 1 0 minus 1/5 0 1 19/40th 0 0 0 times x y z is 0 0 0. Let me write this thing in ordinary notation like you would write it in high school or middle school. Then it will be a good review for us what we did at the beginning of semester. Taking this and multiplying by that, I get 1 times x is 0 times, so let me write 1 times x, 0 times y, minus 1/5 times z, right hand side is 0. Then second row, 0x, 1 times y, 19 times 40th of z, that's equal to 0. Last equation, weird equation, but that's a good sign. Last equation says 0 equal to 0. That doesn't tell us anything other than the fact that you can take one of these guys as a free parameter. So we start from the available ones. Z equals to, let's call it t. Y becomes minus 19/40th of z. Z is t. And x is, it just goes to the other side, so it becomes plus 1/5 of z, and z was t. So then we said we're going to pack this thing as a vector x, y, z. I can take the t out, so I have 1/5 minus 19/40th, and then this is just 1. For any t other than 0, this is going to be our eigenvector. Okay, I can choose t anything I want, just don't choose 0. Well, what's going to make my life easy? I choose t to be 40 so that all of my fractions go away. So that's just for my convenience, has no significance to the there's no really good reason other than we're just too lazy to carry a bunch of fractions on our neck. And so we said for this one, my eigenvector became, okay, so I take t equal to 40, multiply, I get 8 minus 19/40. Let's label our things. So land of 1 as our eigenvalue. Let's call this thing v1. 8 8 minus 1940. That's our eigenvalue. This is our eigenvalue. This is corresponding eigenvector, just one of these things. And then eigenspace will be a line that lines up with this vector in 3D. And it's going to be pretty hard to draw. Maybe we have to go one of the softwares, but we're not going to gain much from it. So 8, we are supposed to go 8 in this direction, 19 back in the, so 8 in this direction, 19 in negative y direction. This is my x and my y, my z, and the z I have to go way up. I don't even have room for that. So something like this is a representation of our v in 3 dimensions. It's going to be a little bit hard to do that. Then the line that lines up with that vector is going to be your eigenspace. Okay. So we survived the algebra. Now the question is, what is it that we did? I mean, it's possible at this point you're kind of feeling queasy and such. So what is this? What it is, this is the vector that if you multiply by this original matrix, it's gonna stretch by a factor of -6. Minus means it flips to the other side, and 6 means it's going to be 6 times taller or longer. Let's go and do actual check. So how do we check? Take the original matrix, which was what? Which was 4, 0, minus 2, the original matrix. Okay, the original matrix that we had here, not the one minus land. Okay, 4, 0, minus 2, 4, 2, 3, 5, 0, minus 7. Is that right? Let's see. 4, 0, minus 2, 4, 2, minus 3, 5, 0, minus 7. You remember we said at the beginning of semester we have the curse of dimensionality. You have so many numbers floating around you. That's what you sign up for, is that right? So 8 minus 19, 40. So what are we writing here? This is my m, this is my v1. Now let's go ahead, patiently multiply. 4 times 8, 32, 0, 80, what's that? Well, that's minus 80, is that right? So it becomes minus 48. Good sign so far. This is minus 6 times that. Let's do the other one. 4 times 8, again 32. 2 times minus 19, it's minus 38. So far, minus 6. And plus 120 makes 114. Next good news, this is also minus 6 times that. Final. 5 times 8 is a 40. 0. Minus 280. I have minus 240. Minus 240. Good news. You can factor a 6 out of this. And what you get is 8 minus 19 and 40. This is the special vector that when you multiply by original matrix, it becomes minus 6 times bigger. That's minus 6. So it stands to reason to call this a special vector. Special in German is Eigen. So you found your eigenvector. Of course, if you had chosen any other t, any other multiple of this, same thing would be happening, but they don't count as different eigenvectors. They all fall in the same class. They're all sitting on the same line. Okay. We found the answer corresponding to smallest. Maybe I go and do the largest as well. It's going to be just like that. So lambda is equal to, largest was 3. So let me see. I need to well, I need my m minus lambda. I'm going to be putting the my next lambda here, so let me go ahead and rewrite it. uh, my lasso is supposed to work, but every now and then it doesn't. So my m minus lambda, remember, was 4 minus lambda 0 minus 2, 4 2 minus lambda 3 5 0 minus 7 minus lambda. So m minus 3 times identity is same. Again, some books put the identity, some books don't. It's the same. So this, when lambda is 3, this becomes 1, 0, minus 2, 4, what's that, minus 1, 3, and then 5, 5, and this is going to be minus 10. Is that right? The null vector of this is the eigenvector of the original. So we are solving the following. Again, 1, 0, minus 2, 4, minus 1, 3, 5, 0, minus 10 times x, y, z is equal to 0. Okay, normally this type of equation, the only answer it has is just 0, but we have arranged these numbers using this special eigen number so that it allows things other than the trivial solution. Again, how do we find it? Your choice to do it by hand or going to this lifesaver here. We have, so if you want, you can reset always and restart. Let's see, that was the previous problem, so I restart, edit, come here. I have 4, 0, minus 2, this is not 4, is 4, 4, no, it's supposed to be 1, 1, 0, minus 2. Let's make sure we are not entering the wrong number. Minus 1, this was 3, this was 5, this was minus 10. Are we right? Let's see. 1, 0, minus 2, 1, 0, minus 2, 4, 1, minus 3, 4, 5, 0, minus 10. Okay, we are in business. This is 1 already. I don't need to reduce it. It eliminates this one, eliminates this one, and again, good news. We got zeros all across. Let's make everything standard. Let's make this thing 1 also. I divide by itself, so I get that. Now let's go ahead and write this matrix on paper and follow the rest of it we are going to do by hand. Okay, so that's a minimal amount of work left to finish this. So 1, 0, minus 2, 0, 1, minus 11. So I go write this. So I have 1, 0, minus 2, 0, 1, minus 11, 0, 0, 0 times x, y, z is equal to 0, 0, 0. That's what we are solving. So we have reduced it to this. Write it so that you see what's going on. So it becomes x minus 2z is equal to 0, y minus 11z is equal to 0. Last equation, just 0 is equal to 0. So it stands to reason to call z to be some parameter t. Y becomes 11t, x becomes 2t. So x, y, z is t times 2, 11, 1. Best choice for t now is just 1 because I don't have any denominators to try to get rid of. So lambda number 3 was 3. Eigenvector number 3 is going to be 2, 11, 1. If you want to check it, pick the original matrix, which was 4, 0, minus 2, 4, 2, 3, 5, 0, minus 7. We are going back to m, not m minus lambda, m, the very beginning, just as a check, not using any intermediary writing. So that gives us a little bit better check. Times, so m times v, the third eigen 2, 11, 1. So 4 times 2 is 8, 0, and the minus 2, that gives me a 6. Good news, this is triple of that. Next, 8, 22, and 3, so that's 33. Again, good news, this is triple of that. Last, 10 minus 7, that is 3. So, as we expect, this is triple of the input. Okay, not every vector is going to have that kind of a special property. This is an eigenvector, so it does have it. Eigenspace, it's sometimes called E3 or something. Several ways of writing. One is to say all multiples of this, t times 2, 11, 1. Another way is to call it the span of these vectors, 2, 11, 1. Another way of referring to it is try the best we can in drawing it. 2 steps this way, 11 steps this way, 1 step up, so kind of like this. And then the eigenspace is the line that sits on it. So several ways of talking about it. You just look at the web assignment, see which one of them it's compelling you to write. Okay, so we did there were 3 of them. I did the smallest one, the largest one. Let's finish the job by doing lambda equal to 2. You have to do everything all over again. So you notice that these problems are kind of long in the tooth. It goes on, and you have to do a few of them to be able to do this thing quickly and be able to finish the job in a reasonable amount of time. Of course, you're not writing as much or explaining as much, and then you have the software, so it can be done. Okay, with respect to lambda, so middle guy is lambda is equal to 2. M minus lambda, one more time. M minus lambda was 4 minus lambda, 0 minus 2, 4, 2 minus lambda, 3, 5, 0 minus 7 minus lambda. So m minus 2 is going to be 2, 0 minus 2, 4, 0, 3, 5, 0, and this will be minus 9, I believe. What is the eigenvector of that one? Well, let me give you a shortcut for this one, for such a long problem. The eigenvector is something like this with zeros on one column is going to be 0, 1, 0. That's also, so shortcut 0, 1, 0. 0 corresponds to this column, this 0 corresponds to that column, 1 corresponds to those zeros. How's that? Let's just go explain it in the context of this software again. So I had what? 2, 0, minus 2, 4, 0, 3, 5, 0, minus 9. Let's go do this thing again. So reset. We're starting a new problem. Edit. uh, 2 0 minus 2 4 0 3 5 0 minus 9. Okay, a bit weird because of those zeros here, but we can do it. Divide by that, eliminate this, eliminate the last one, divide this one, take this, eliminate item above it, eliminate item above it. Notice that for echelon form, we insisted on having all the zeros at the bottom. You can leave it like this, but if you want to do an echelon, you have to exchange row 2 and 3. Did you listen to me? Come is not doing it. For some reason the software is not flipping the rows, but it doesn't matter. We just go ahead and do that ourselves. So I did where were we? Okay, sorry. So you have to solve the following, just like the other one. 2 0 minus 2 4 0 3 5 0 minus 9 times x y z is equal to 0. Okay, we cleaned it up. It became like this. So somehow my software there was not, maybe my computer was not flipping the rows. 0 0 1. Is that right? And that's what we had when we cleaned up. This is what we got. Okay, we just use that. Just go ahead and write it. The first one, 100 times xyz, you get what? X, right hand side is 0. Second equation, on the left is 0, on the right is 0. Last equation just reads z is equal to 0. This equation, due to its simplicity, is going to trip you. Now, x is 0. There's no other choice. Z is 0. There's no other choice either. The only choice left is for y. Y can be any number and still that equation is valid. So my y is my free parameter. X is not free and neither is z. So if you want to take x, y, z and write it, if you want to insist to think about it as 0 times t, and the 0 times t here, you still can factor it. T is 0, 1, 0, which is what I said at the beginning. Your eigenvector now, so for lambda equal to 2, the eigenvector turns out to be 0, 1, 0, and easy to graph the eigenspace. At least this one is easy, because if this is x and this is y and this is z, my eigenspace is just sitting right on the y-axis. The y-axis is my eigenspace. So several ways of talking about the eigenspace. All multiples of that, meaning just this, t times 0, 1, 0, except that t equal to 0 is also allowed here. Another style of talking about this thing is calling it span of base of eigenvectors, or just y-axis in this case became a simple answer in this situation. Okay, so let's go back and see what happened. Main ideas. 3 by 3 matrices come out of situations where you have 3 particles interacting. The more particles, the bigger the matrix, the more work has to be done. You notice that this is not going to be the way to do this thing in for big system, because it's going to be absolute torture trying to do this So it's more for smaller situations. You do come across this in some application. Bigger ones, there are specialized software to do this thing for us. Of course, you need to have a basis of mathematics to understand what the software is doing. But anyway, so step one, we have three goals: finding eigenvalues, eigenvectors, and eigenspaces. To find eigenvalues, step one, determinant of m minus lambda equal to 0. Subtract lambda from the diagonal, find the determinant of this, set it equal to 0. Heads up, this is going to be a cubic equation, not the easiest thing in the world to solve. Look for some easy way of factoring it. So whatever you learn in college algebra is going to come in handy for you. In this problem, it's almost factored for you. So 2 minus lambda was a factor, and the rest of it we managed to factor easily. So that made our day, in the sense that these eigenvalues are easy to find in this case. Step 2, how about the eigenvectors? Step for that, find the null vector of m minus lambda. So we subtract one of these lambdas from the diagonal entries. We have a new matrix. Find a vector that when you multiply this, you get 0. Of course, 0 will do it, but we are looking for a non-trivial answer. So x, y, z cannot all be 0. Okay, so we use the software to do that, or you can do it by hand. We do this thing 3 times for each of the lambdas. For each case, we get the eigenvector, and the eigenspace is the line that lines up with this. More complicated problem, the eigenspace could be a plane and so on. Hopefully in the next example we are going to take a look at that. Every time we find one of these eigenvectors, we check it, take the original matrix times the eigenvector. Out should come that eigenvalue times the eigenvector. That will check our answer. Okay, I realize was a lot of algebra. That's why I put the application first, and hopefully you're motivated to do this, to handle 3x3 cases in engineering. Okay, until next time, good luck and God bless.